a hostile flag of conquest, but by a banner of freedom and peace. We have vowed that we shall not see space filled with weapons of mass destruction, but with instruments of knowledge and understanding. For space science, like nuclear science and all technology, has no conscience of its own. Whether it will become a force for good or ill depends on man. But I do say that space can be explored and mastered without feeding the fires of war, without repeating the mistakes that man has made in extending his writ around this globe of ours. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
It's one small step for man, one giant leap for mankind.
When it comes to understanding the universe, we are only beginning. Humankind continually searches for patterns, trying to figure out, what is the universe made of? How does it work? How does our planet, our solar system, our galaxy fit in with the other pieces? And what don't we know yet? Helping us discover more pieces of the puzzle will be a new instrument on board the International Space Station, called the Alpha Magnetic Spectrometer, or AMS. AMS is not a telescope. Rather than looking at space, it will sift through space, studying the high-energy particles of cosmic rays. From the unique vantage point of Earth orbit, the AMS experiment has the potential to answer questions about the origins of our universe. The study of high-energy particles might help in the search for dark matter and antimatter in the universe. Nobel Prize-winning scientist Professor Samuel Ting, well known for groundbreaking particle physics work on Earth, has collaborated with an international team to create the Alpha Magnetic Spectrometer, a high-energy particle detector that takes particle science into space. With over 300,000 data channels for detection and over 600 onboard microprocessors to analyze the data, the AMS is sponsored by the Department of Energy, and scientists from 16 countries lent their expertise to create it. Parts from around the world were sent to CERN, the European Organization for Nuclear Research, in Geneva, Switzerland. NASA had the job to figure out how to get the 15,000-pound experiment into Earth orbit and have it operate in the hostile environment of space. The AMS was finally sent to the Kennedy Space Center, where it was ready to fly on board a space shuttle, the final large component of the space station to be sent on one of the last shuttle flights. Part of the shuttle crew is European Space Agency astronaut Roberto Vittori, who will operate the shuttle arm to grasp the AMS from the shuttle payload bay.
That means that I will have the responsibility with the shuttle robotic arm to take it from the payload bay and offer to the station. But behind that specific operational task, there is a very long history. I started about 20-25 years ago to study physics, to think about space, to think about the universe. And the specific of the search of the antimatter was one of my main and deep interests. It may appear as a very strange coincidence that today I will be the one to take this unique piece of hardware, take it from the bay of the shuttle and give it to install on the station.
For the AMS, there are many benefits to having a fully functional space station as your home.
So AMS weighs 15,300 pounds. Most of that is science experiments. We do not have to carry our own power. We do not have to carry our own data systems to transmit that data back to Earth because all of those systems are provided to us by the space station. It's a perfect example of how you can utilize the capabilities of the International Space Station to fly groundbreaking science experiments.
So how exactly does the AMS work? One thing it is not is a telescope. Telescopes measure photons, packages of light, both visible and invisible to the naked eye. This type of astronomy has given us most of our knowledge of the universe thus far. But the cosmos speaks to us in languages other than light. For the AMS, this will be the first time scientists study charged particles. Exploding stars and other celestial phenomena are thought to produce cosmic rays which travel across the universe and can wash up on the shores of our planet. The rays are composed of charged particles, but many of these are absorbed in our atmosphere, making it impossible to study them on Earth. But outside our atmosphere, on the space station, the AMS will be able to sift through these particles, helping us search for antimatter, dark matter, and the stuff of which the universe is made. A particle will pass into the AMS. Layer upon layer of detectors tells us the mass, energy, and velocity of the particle. Other detectors tell us which direction or path the particle took as it passed through the AMS. At the heart of the unit is a magnet that will make the particle curve one way or another, telling us whether it is matter or antimatter. And just how quickly does all this particle detection happen?
Faster than I can snap my fingers. Nanoseconds. In nanoseconds. AMS gathers data at a ridiculously large rate. We will see about 25,000 hits per second of cosmic rays coming into the aperture of AMS.
8, 7, 6, 4, 3, 2, 0, and liftoff for the final launch of Endeavour, expanding our knowledge while expanding our lives in space.
Houston, Endeavour, roll program.
Roger, roll, Endeavour.
Houston is now controlling. Endeavour beginning to pull over onto its back. The roll program underway as Endeavour begins a heads down position on course for a 51.6 degree, 136 by 36 statute mile orbit. Three engines now throttling down as Endeavour passes through the area of maximum dynamic pressure on the vehicle in the lower atmosphere. Approaching 1 minute into the flight.
Endeavour, go at throttle up.
Roger, go ahead, throttle up.
Endeavour's three main engines now back at full throttle, all three engines in good shape. Endeavour's already traveling 1,300 miles per hour at an altitude of 11 miles downrange from the Kennedy Space Center, now 12 miles. At liftoff, Endeavour fully fueled, weighed 4.5 million pounds. It's already lost half that weight in propellant now, burned that weight. The next event is burnout and separation of the twin solid rocket boosters. That upcoming here shortly at the 2-minute 3-second point. Those boosters are burning 11,000 pounds of fuel per second. And standing by for separation of the solid rocket boosters.
Now you can see Venus.
Do the astronauts go there?
Not yet. Maybe someday. In fact, there are some really smart scientists who are working on something called antimatter to power spaceships into deep space. And all the fuel that they'll need, well, it'll fit in something about like this.
Cool. Where do they do that?
Washington State University.
Go Cougs.
Washington State University, because the world needs big ideas.
At any given moment, about 1,800 thunderstorms are in progress somewhere on the globe. New observations by NASA's Fermi Gamma Ray Space Telescope show that thunderstorms make antimatter. The process starts with a terrestrial gamma ray flash, or TGF, an intense pulse of gamma rays originating from thunderstorms. These dots mark TGFs observed by Fermi's Gamma Ray Burst Monitor during the spacecraft's first 8 months of operations. Researchers estimate that there may be as many as 500 TGFs each day. On December 14, 2009, as Fermi passed over Egypt, it spotted a TGF produced by a thunderstorm in Zambia. The TGF was over the spacecraft's horizon, where Fermi couldn't see it. So how could Fermi have detected it? Scientists believe that the TGF process begins in a thunderstorm's intense electrical field. Electrons within this field become accelerated upward. Above the storm, where the air is thin, the electrons can ramp up to speeds nearly as fast as the speed of light. When these ultra-fast electrons encounter an atom, they emit gamma rays. Very rarely, one of these gamma ray photons grazes an atom and transforms into a pair of particles. One, an electron, is normal matter. The other is antimatter, the electron's opposite, called a positron. The gamma rays travel in straight lines, but the charged particles spiral along lines of Earth's magnetic field. And that was the route to Fermi. The particles created by the TGF rode upward on magnetic field lines, and then struck the spacecraft. The positrons annihilated when they struck electrons in Fermi, creating a flash of gamma rays. For an instant, Fermi became a gamma ray source, and set off its own detectors. A fraction of a second later, some of the particles were bounced back along the same magnetic field line. They again passed through Fermi and again produced gamma rays. The spacecraft has observed this phenomenon on at least 4 other occasions. So the next time lightning flashes and thunder roars, remember, you may be witnessing antimatter in the making.
Researchers have found a band of antiprotons ringing around the Earth, adding one more to the list of particles Earth holds within its magnetic field. Cosmic rays constantly rain in from space, colliding with Earth's atmosphere and creating a spray of new particles. Scientists have observed antiparticles before, but this is the first time antiprotons have been observed. Many of these particles become trapped inside Earth's Van Allen radiation belts, the donut-shaped zones around Earth where particles swirl around the magnetic field. The find, described in Astrophysical Journal letters, confirms theories that predicted the particle. The University of Rome detected these particles using Pamela, a cosmic ray detector attached to a Russian satellite. The satellite orbited through the South Atlantic anomaly, allowing the study of geomagnetically trapped particles in the inner radiation belt. Between July 2006 and December 2008, Pamela detected 28 antiprotons trapped in the spiraling orbits around the magnetic field sprouting from the Earth's south pole. According to researchers at Italy's University of Bari, the band is the most abundant source of antiprotons near the Earth. The find could one day open the door to fueling spacecrafts with the exotic particle, an idea already being explored by NASA's Institute for Advanced Concepts.